And contained in it, entirely contained in it, would be an empty space. And this empty space or negative object could be classified as a void. A hole is partially contained within a positive object. And again, as you can see here, a two-dimensional version, and this is only kind of one example of the shape of a hole, is only partially contained, which means that we have this one opening. So it also contains walls and a base. Walls would be connected to the opening, and then the base would be connected to the walls, but contained within the positive object. So the last type of negative object that we have is a tunnel. And this is a negative object that has only walls and no base. What this means is that if you were to choose to enter from one area, you could leave from a different area while traveling through a positive object that contains it. So again, walls would be connected to these openings, and we don't have a base, so it's not there. So, and again, this is only one example of what a tunnel could look like. So why are negative objects so crucial to study? And as I mentioned in the beginning, search and rescue, otherwise known as SAR, and particularly urban search and rescue, which is just search and rescue in urban areas, negative objects are really important. So because urban areas have an increased disaster frequency, that's due to development being located near chemical plants or nuclear plants, because that's where jobs are, as well as higher populations, which leads to more frequency of terrorist attacks. These disasters can cause buildings to collapse or structures to change and then trap people inside, potentially, or just create a very dangerous area. So these collapsed buildings are called rubble piles. So this would just be like the building crashes down and then everything that the building was made of falls into this random, unstable structure. So if we understand negative objects, we would have a better understanding of this rubble pile, because when the building collapses, new areas inside, so new voids, as well as new openings on the outside are formed, and those are all negative objects. And currently we don't really understand them. On top of that, if we understand rubble piles, we can understand how to stabilize them, but we can also speed up the process of flagging important areas of the rubble pile. What this means is that we can identify areas such as access holes, which is talked about in a paper by Chris Kong. And these are areas where response personnel can actually go into the rubble pile so they can save people that have been trapped inside. So this here to the right is an example of a void. And this is created by, this is like a schematic of what a GPR, ground penetrating radar, would see, and this would be entirely enclosed within the rubble pile. So the biggest reason is the speed here, and that's because currently response personnel have to search these collapsed buildings, which are generally very large. They have to search them by foot, and that can be very time consuming. And every second counts within a search and rescue mission. Another big reason for us to study negative objects is that it can affect path planning algorithms. And path planning is used with respect to autonomous traversal, all these self-driving cars we see nowadays. They need to understand if the road is safe to travel on, where safe roads are, and something like a pothole in the ground is a negative object that they don't entirely understand how to classify or even avoid at the current moment. So by understanding negative objects and being able to classify them, we can actually increase full speeds of autonomous robots, and we can create more accurate path planning algorithms. So these kind of go hand in hand. So a good thing to point out right now is that a lot of robots use something called LiDAR, which is just like something that shoots out a bunch of lasers to measure the distance that that laser traveled. So from now on, I'll just refer to it as like a laser rangefinder. And what that does is it creates like a point cloud. So this picture on the left is just a point cloud of a bunch of dots. Not a bunch of dots, but this will represent like the ground in front of a robot. And a negative object actually doesn't produce any feedback to these sensors. So what happens is researchers have to infer where the negative object is. And in this case, they inferred it as this gap in data. But you can see even in this point cloud, here would be where the robot would be. So all the points are very dense. But as you reach farther and farther out, the points become more and more sparse. So you can notice here that the spacing of this negative object is actually almost the same as the spacing between these 2 points. So it's possible that there would be a negative object that lies here, but we wouldn't be able to see it. And to kind of emphasize this point a little more, because we can't plan too far ahead, our robots have to move very slow. And so we can plan each time we are able to see a negative object. And again, so to make this point even more clear, imagine there's a robot standing in the center of these rings. So 16 meters out of the, like in front of the robot in any direction is about as far as you can see before the robot really doesn't know what's going on. So everything that you see here that's yellow is a false positive, or the robot thought there was a negative object there, but it was actually nothing and potentially safe area. So understanding negative objects would help us to increase that range. So what are some challenges to classify negative objects? Well, I briefly talked about one, and that's hardware. Because negative objects are just empty space, sensors can't detect them. So as you can see here, what you would think to be the negative object would be this dotted line here, but because it's just empty space, our laser would actually go right through it and hit the wall of the negative object. And that's not always super useful because it doesn't always tell you exactly how far from the robot it actually is. And another big problem is something called occlusion. Occlusion occurs when a positive object blocks items after it, so you can't get data there, but it's not because it doesn't exist. It's because the data that would be there has been blocked. So in this case, these are examples of negative objects. We can imagine that it starts at the tip of this point here, and there could be an area afterwards that's safe, and this might not be that deep, but because this area is occluded, we can't see anything in this yellow triangle. So for example, this yellow triangle would start at this corner and then reach all the way to about here. So we don't actually get the true depth of the negative object, and we also don't get the true width of the negative object, again, because some of these points might not lie directly on this corner. Following that, we could also just occlude a downward slope. So it might be safe for a robot to travel, but because we can't see anything lower, we would just automatically make it not safe. And then that would increase travel time depending on how far the robot actually has to go, and if it changes direction because of it. Another challenge is consistency. So like I said before, there really isn't a good way to talk about negative objects. And because of that, there also isn't like any vocabulary between fields. So what this means is that for someone, a negative object could be defined with a set of features A, and for someone else, it could be defined with a set of features B. It might be completely different. A really good example of this is an approach to identifying road imperfections, specifically potholes, by Erickson in 2008. And what he did was he called this a pothole, as well as this sunken in manhole cover. And on top of that, this bridge joint, which is actually a positive object. Now, their approach was using accelerometers. So differentiating between negative and positive objects is quite hard, but the key here is that he identified all three of these as a pothole. Now, later on, Wang in 2015 used the same approach, just like obviously upgraded some of the calculations in the algorithm, but they only called this a pothole. And this being its own this own type of negative object doesn't really compare to this, and especially not this bridge joint. So in comparing these two, specifically in Wang, they compare their algorithm to Erickson. You're not actually getting an accurate comparison between algorithms, so you can't effectively compare the algorithms or even their performance. There's also no effective way of describing features of negative objects. So we can say this is sunken in, but we also don't there's not really a way to talk about color or apart from depth. That's kind of all we have when it comes to negative objects. And there could be new ways to find features, but the field just hasn't developed enough to identify any. And to further this, there aren't any set boundaries between different types of negative objects until my proposal of the 3 types of negative objects. And this is a problem, again, because if you identify this as a pothole and this is a pothole, who's to say that they're different and who's to say that they're the same, because there isn't anything widely accepted. So the bigger question is, where can we go with negative objects? And this is all future work. So this is a pretty open field, especially because there hasn't really been a ton of research on it. So the first thing that we would need to do is develop a lexicon. The framework for this would be to treat, my 2 ideas for that would be to treat negative objects based on the shells of their bounding positive objects. So like I mentioned before, we could identify this as a tunnel. But to be more specific, we could call it an elbow tunnel. And that's because its bounding positive object is an elbow pipe, or in the shape of an elbow, similar to how you would bend your arm. And another option would be to treat negative objects as their own type of object and work towards negative object specific classification. So this could be by functionality, could also be by some features that we haven't determined yet. A really good example of this is the definition of a manhole. And the function of that is literally to put a man in it. So that is the functionality, and that is how they're classified. So we also have other ways to develop this field, and that would be trying to develop classifiers. And how could we develop our classification? Well, we could try incorporating multiple sensors. So that would be like using LiDAR or that laser rangefinder to get a point cloud of the general area, and then incorporating a second sensor to get past that occlusion, something like ground penetrating radar, so they can more accurately identify what negative objects lie in the way of a robot trying to do autonomous traversal. We can create a data set and then use different techniques such as computer vision or just simple image analysis, stuff like identifying certain areas based on their color or the brightness. So creating a data set is definitely a good starting point. And then computer vision, which is where I plan on focusing my efforts, to use just like simple images and then trying to get a computer to identify certain features that I might not understand or think about off the top of my head. So machine learning is definitely a way to go as well. Even more so, we can incorporate negative object research into different applications. So this would be like trying to create algorithms for search and rescue or urban search and rescue to identify those access holes, or to help try to work on identifying holes and to better some of the algorithms that already exist. With respect to mining, we can also better their ability to communicate with each other by classifying the types of mines or the structures you have to build in mining. And that's because mining is literally creating negative objects to put people inside of or withstand vibrations while people are inside of it. So that is a very important application of negative objects. So better understanding them would be a way to better increase safety in the field. Glasses for visually impaired is a paper and an application proposed by Hergulayu. And this takes images like common things that somebody would see on a regular day. So maybe going to the GO train or just walking and there being like a missing manhole cover. Even a flight of stairs is an example of a negative object. While they only work on identifying negative objects based on depth change, there might be other features, and having a classifier might better their ability to identify edges of negative objects to kind of create those boundaries and warn people that are visually impaired. And finally, we can also introduce classifying negative objects into road maintenance monitoring. And what I mean by this is there's a lot of papers proposed on identifying potholes. And with the upcoming boom in autonomous driving and all these cars having cameras and a lot of sensors everywhere, and everything being connected to the internet, you could potentially create a system that tracks potholes on the road or any other road imperfections and rates them on severity as well as frequency of driven over, and then help to create a better, more efficient way to fix all those annoying potholes that everybody hits. So now I'd just like to do a quick recap and talk about the takeaways from this paper, and that is, what is a negative object? Well, simply put, it's the absence of a positive object. And I suggest 3 subclasses, which are holes, voids, and tunnels. Why should we care about this? Well, it has major applications in urban search and rescue, as well as any autonomous traversal. And finally, there is lots of room for research development, which is always a good starting point. And they literally consist of the other half of the objects in the world. So understanding them would help us understand a lot more in today's society. And that's it. Thank you.
Thanks so much, Katrina. Actually, before we continue, I want to give everyone a little bit of information on our speaker. Katrina is in her final year for computer science master's at Ryerson University. She actually holds an honors BSc from the University of Toronto with a specialty in physics and a minor in mathematics, which is insane, so impressive. Her interests, as you may have seen, do lie in negative object research and imitation learning for chess engines. And she works with Dr. Alex Furman as well, who's here in the audience, and she works to build a lexicon and classifier or negative objects. I can get started on the questions. Sorry about that. This work is kind of insane that people aren't more invested in this with how much we're already investing in this, or like with autonomous driving and so on. I'm just curious of the current classification system that you have built. Um, is this something like if we only have access to just images or like two-dimensional things, how does that relate to a three-dimensional field like what you're working in?
Yeah, so actually, that's going to be what I'm going to work on with my thesis. So I'm currently just building a data set of like regular images with like crappy cell phone image, which isn't like crappy considering how much cameras have come along. And the idea would just be to like use machine learning first to kind of say, is a certain type of negative object in this picture or is it not? So I'll be pre-labeling based on my suggested suggested subclasses. So mostly I'll be focusing on holes just because tunnels and voids, well, voids you can't exactly see, but tunnels pose a little bit of an extra challenge because they can bend and turn, and that always causes some problems.
Right. Yeah, thanks.
No worries.
So I see Dr. Furlan has a question, and then you can go ahead.
It's just a suggestion, actually. So I've seen this stuff before, but it just inspired me a bit to think. So one form of a tunnel, or perhaps it's its own class of hole, but I would say it's probably a tunnel, is a path or a way.
Mhm.
So you should consider that, because especially in machine vision, when you're talking, like a lot of their work is on wayfinding, finding a path through things, but inevitably they kind of do a two-dimensional view of it, which is not sufficient for like tall people going through short places.
Yeah.
The notion of it as being a whole might be benefit.
Yeah, and I mean like that's what I was bringing up with respect to that proposal for like it's stereo vision for visually impaired. So it's a pair of glasses with some like little cams on it. And what they do is they basically they take these two images and they overlay them to try to get like a depth measurement. And then they basically like try to fit a plane, and then anything below 15 centimeters underneath that plane is considered a negative object. But they don't classify the type, and so they're really just looking for edges. So as soon as it goes back up or it extends beyond a certain area, they kind of just highlight that and call it a negative object, but they don't really understand what it is. Yeah, so.
Thanks for the
Hi,
answer.
Katrina. I have a question for you. And
Yeah.
thanks for the presentation. It's my first exposure to negative objects. I'm still having a bit of trouble getting my head around it. You say that a negative object is kind of the absence of positive objects. I would assume that positive objects can exist without negative objects. And what's the difference between a negative object and a positive object that's void of content, like an empty jar?
Yeah, so the jar itself, as in like the glass, and you can basically take like a dot and then trace it up and then in and around the glass. That glass itself would be the positive object. And inside the jar, imagine if we put a lid on it, inside the jar would be a void. And if we took the lid off, then it could be a hole. So negative objects can be like multiple different classes based on their bounding positive object.
Right. So
Does that clear it up a little more?
A negative object still needs a positive object to provide boundaries. Is that correct?
It like, again, so some of it is a little on the hand wavy side, which is why they're just suggested classes. But in general, so holes, tunnels, and voids rely on boundings. So like the positive object must bound that area in order for it to be classified as that. But like something as simple as air is really a negative object. It's just an empty space, and you can put a drone in it or fly an airplane through it. So that might be its own type of negative object that I just don't have a classification for yet, and which is why this field needs more development.
Yeah, it's a fascinating field. It's great. Thank you very
Yeah.
much.
Yeah.
Just add to that. I don't want to take up a lot. The reason we started looking at, we just called them holes before, is because the problem of positive space was intractable on rubble. So I thought we could characterize what rubble was, and I spent a couple of years on that and decided it was impossible. So we decided to do the opposite of that and worry about the stuff that's not there. And there's zero nomenclature for this. So I'm glad that I have a physicist as a graduate student who kind of can look at this from a completely different perspective, right? So we need that because you're right, Steve. Space, for example, is a negative object, but it's not a useful negative object in our parlance, right? So I'm interested in one specific aspect of this, except I need to have nomenclature around it to kind of explain it to anybody, right? So
Right.
we're just at the start of this.
No, it's fascinating. Very interesting.
Yeah. So like focusing on the bounded negative objects, it becomes like a lot more applicable, and it becomes much more useful to everybody else because you're always running into things, or like your house, all the rooms, like those are bounded areas. And they're areas that everybody kind of talks about. Nobody really talks about open air. So like specifying negative objects is really important. Again, like without nomenclature, how do you specify anything, right?
Yeah, and your timing's perfect with robotic technology and robots, even the ones that go around your house cleaning floor. Like they don't know how to handle that. It's so it's great timing.
Yeah.
All right, thanks for the presentation again, Katrina.
No worries.
We can share your email if there are additional questions. I